Okay, so before we start going on to a new lesson on lesson 8, we're going to spend time doing whiteboards. So if you can just pause this video, take out a sheet of paper, I would like you to find the final temperature of the metals. Okay, so pause the video and then I'll take it out. Okay. So they tell you have a piece of metal that have a mass of 250 grams. So remember, you have to change it to the SI unit. So the mass for the metal is 0.250 kilogram, which is 350 degrees Celsius, and it's placed in 1 liters of water at 23. The metal has a specific heat capacity, which is your C, of 450 joules per kilogram degree Celsius. Water is 4180 joules per degree Celsius. Find the final temperature. So my suggestion, 2 different colors. So I have the mass of the metal. So the metal have a mass of 0.250. Initial temperature was 350. The water, I'm going to use blue, has 1 liter, meaning 1 kilogram, because density of water is 1, so you can just do a direct conversion. So T1 is 23 for the water. The metal have a specific heat of 450, and the water is 4180. And they want you to find final temperature. So key thing to remember, the T2 are the same for the two objects, and the heat exchange, meaning heat loss from the metal, it's the same as the heat gain from the water. Okay? So heat lost, which is from the metal, adding the heat gain from the water is equal to 0. That's what you start off with. You don't have to write these things out, but I know that Q is MC delta T, and I also know that delta T is T2 minus T1. So I'm going to sub it into each of the equation. Right, so plug in the information from what we had. So change it back to the red. 0.25 with 450 being the C. T2 is my unknown, minus the T1 initial temperature of the metal was 350. And then the water, the mass was 1K. 4180 is the C. And final temperature is my unknown, and the initial was 23 equals to 0. So expand it out. So multiply the 0.25 times the 450. So 122.5 into the bracket. So we're going to be expanding after. So this one is already 1, but I'm just going to write this out. Okay, so the next thing now, you're going to do the expanding into the bracket. Okay, adding 4180 T2 minus 96140 equals to 0. Okay, so collect your like terms. Put the T2s on one side. And then move all your numbers, all the non-T2 one, over to the other side so they all become positive. So I added the number part, and then now I'm going to add the T2. So 429.2, 4292.5 T2, divide both sides by that. So the temperature I got was, say, 32 degrees Celsius. Sig digs is 2. So I found the final temperature to be 32. Okay, so review of lesson 7. We've been talking about, say, for example, if I have water, if I put in some heat, I am able to increase the temperature. The equation that we use is called Q equals mc delta T. And in particular, if this is water, what happened is we would use the specific heat capacity for water, which is 4180 joules per kilogram degrees Celsius. Okay, we have this thing called the heating curve. What the heating curve is, we find out what is the temperature at a certain time when I keep inputting the heat. Okay, so if I have water, say for example, I'm just making this up. Okay, say for example, if I tell you that I have this water that started off at 10 degrees Celsius. So I am at 10 degrees Celsius. Okay, and the water was whatever the temperature is at a certain time. As I put in the heat, as I am burning this, so I'm putting in some sort of heat, my temperature is going to go up based on the equation, right? The more heat I put in, the more change in temperature. Okay? Now the problem arises when we're talking about, see how in here it says state of matter, where in the changes of state, the weird thing starts happening. If I keep heating it up and eating it up, I know that it has been water the whole time as I'm heating it, but it will get to this point that the water no longer stays at water. Okay? The temperature special one that we would be dealing with it at 100 degrees Celsius. What is happening at 100 degrees Celsius is that we now have this changes of state that's happening. Okay, so all of a sudden we go from liquid to gas. Okay, we call it the evaporation, right? And what the law of physics has been telling you is that as I increase the heat, temperature change regularly. But during a changes of state, what happened is even though I keep putting in the heat, there's actually no change in temperature. Did you put in the heat? Yes. But the heat is now not used to change the temperature, but it's actually used to change the state. Okay? We call this the latent heat. Okay, what happened is the equation now got changed. We no longer use the equation Q equals mc delta T. I know I'm putting in heat, but my delta T is 0. That doesn't mean 0 heat is done. What happened is it means that that heat energy I've actually used to evaporate and turn the liquid into gas. Okay, and then what happened after that is now when all the water has now been turned into gas, what happened is temperature is going to go up. Okay, my heating curve is back to normal, but now instead of water, it is actually now steam. I am now able to use the old equation, Q equals mc delta T, but the problem is now my C is no longer 4180. My things actually get changed. My specific heat capacity, I now need to use the specific heat capacity for steam. Okay? If we actually go backward and say, well, how about if I go lower than 10? The other special number for water is that if it keeps going down, the other special point is 0 degrees Celsius. At 0 degrees Celsius, that is the change between the ice, which is the solid, versus the liquid. Okay, so now I am now dealing with ice. And what happened is I have another plateau because there is now another changes of state. My equation is still a Q, but this time is called MLF. Okay, I'm going to write this out. LF means latent heat of fusion. Okay, just like the specific heat capacity, it is a constant. And then finally, if I bring the heating curve anything cooler, say down this way, I am back to the old equation, MC equals delta T, but this time we're now dealing with specific heat capacity for ice. Okay, this is called heating curve. And so it depends on where the question is taking you. If I give you a question that say, if I bring water, let me use the pen. If I bring water from 10 to 120 degrees Celsius, there's actually 3 parts to this. So it's almost like if I'm going to bring a highlighter, I start my question at 10, I end at 120, which is up here. What happened is I actually need to find from the first line at 10, I need to find Q equals MC delta T, adding the latent heat, Q equals to MLV, plus the Q equals MC delta T. There's going to be 3 sections that I need to cover. If I change the question, so if I now say, hey, let's not talk about that. Let's say if I want to make this the hardest question that it could, is I have 2 different changes of state. If I actually do this, if I say, hey, how about if I change the question to if I wanted to start with ice, okay, and I go from negative 10 degrees Celsius all the way, I'm going to heat it up, melt the ice, heat up the water, evaporate the water, turns it into steam all the way to 110 degrees Celsius. Okay, see how many different steps of calculations will I have to do. I started off at negative 10, so I'm now down here. I need to first of all bring it up until it's going to start melting. Melt it, so that's your second part of calculation. Bring the water all the way up to 100, evaporate the water, and then finally calculate how much heat it takes to heat up the steam for another 10 degrees Celsius. So the key thing is that you need to know the melting point and the boiling point for the different substances. When you actually do your homework, I actually gave you another question that is, I think, on aluminum. Some of the data are missing, so the textbook doesn't always have it. So if you need to look for any of the constant for the latent heat, you go to the textbook. I gave you section 6.4. If you scroll down, you can actually see that there is a chart right here that will tell you the different melting point and boiling point for the substance and what the latent heat capacity is for each of it, so that you can actually work out what is the total heat that is needed. Okay, so going back to the lesson. All right, so we're going to go through some examples together. Okay, so come back to here. So just little definitions. Please take your time and read through your notes. I'm not going to go through all of the terms. You're asked to do that on your problem set anyway. So what is the latent heat? It's the total thermal energy absorbed or released when there is going through a changes of states. Okay, 2 words, latent heat of fusion and latent heat of vaporization. Latent heat of fusion, for example, for water. If it's for water, the fusion happens at 0 degrees Celsius. That is talking about when you go from a solid to a liquid. So when you're melting, or when you're actually condensing it. Like, so when you're freezing something or when you're melting something. Okay, latent heat of vaporization happens for water at 100 when it is boiling. Okay, so that is the changes of state. And just now I already talked about different substances have a different temperature that it happens. So you kind of need to find out what the melting point and the boiling point for it. Okay. And the equation for them, these are the two new equations. Q equals MLF when it's melting or freezing, and Q equals MLV, boiling or condensing. And just like always, your mass have to be in kilogram. What unit do you think LV would be? Okay, one easy way to tell is if Q equals to MLF or FV, I'm just going to do LF. If I rearrange the equation for LF, it's going to be heat over mass. And I know that Q is measured in joules and mass is measured in kilograms. So the unit for LF would be joules per kilogram. So in the other hand, what that means is you can actually look at the definition. What does that mean? Specific latent heat, capital L, is whatever the substance is going to be different for different things. For water, for aluminum, for ethyl alcohol, they're going to be different. But for that particular substance, the amount of thermal energy that it requires for 1 kilogram of substance to change from one state to another. So how much heat does it require for 1 kilogram of, say, ice to melt into liquid water? That is the specific heat, latent heat, which is measured in joules per kilogram. Mine's kind of off. Okay, so let's go through examples number 1. How much thermal energy, which is Q, is released by 620 of molten lead, meaning in liquid form, to change into a solid. So there is involving a changes of state, and they tell you that the latent heat of fusion is 2.5. So they want you to find Q, and the mass is 652 grams, so that means 0.652 kilogram. Please make sure you convert it to SI unit. And they give you LF, latent heat of fusion, is 2.5 times 10 to the 4 joules per kilogram. So Q is mLF. So multiply those two out. So I got 16300 joules. And taking a look at the 2.5, I have 2 sigdigs. So you can either round it off, or if you wanted to put it in scientific notation, it's up to you. So both are fine. Okay. Second question. Ethyl alcohol is liquid at room temperature. How much thermal energy is absorbed when you have 135 grams of ethyl alcohol at 21.5, so that's the room temperature, heated until it all boil and turn into vapor at 78.3. So they actually came in here and tell you that this is when it's boiling. So this is when the ethyl alcohol would go from liquid and turn into gas, right? So that's why we're using the LV, because that's when the liquid alcohol turns into a steam, okay, a vapor. Okay, so I suggest at cases like that, it's always a good idea to do a heating curve just so you know what sections you're starting off with. Okay, I'm going to mark off the boiling point, 78.3, because this is the one that is going to go at the plateau. That's the one that we're not having any temperature change. Okay, so I know that we start off at a temperature of 21.5. Okay, and it's heating. So as the heating curve is going up, we have this equation, Q equals mc delta T. And in this case, we're going to talk about the C being, they gave it to you, 2.46. And then they also say it is now completely turned into vapor. So that means we actually have to put extra heat in to evaporate it. Okay, so in that case, the other equation is the Q equals mLV. So during the changes of state, even though there is no change in temperature, it still requires heat to actually evaporate and boil off the ethyl alcohol. Okay, so that means this is a two-part question. So Q total is going to be equals to the mc delta T for when it is still liquid, and then adding the amount of heat that it takes to evaporate it. So M, I didn't write out my given. M is 135 grams, so it's going to be 0.135 kilogram. And then I got the C and the LV. And the C is 2460. delta T, I went from 21.5 to 78.3. So I'm going to subtract them. Final minus initial. Okay. And then adding the latent heat, which is the evaporation part. The mass is still 0.135. And then the vaporization is 8.6 times 10 to the 5. 21.5. Okay, so answer, can you double check for me? I don't feel confident. I might have to do this again just to make sure. Check your SIGDIGs. This is still in joules. I have 135, 21.5. But in the latent heat, because I used the 8.6, there's 2 SIGDIGs in total. So 1.3 times 10 to the 1, 2, 3, 4, 5 joules. Double check the answers for me. Okay, try out your homework, and then you should now be able to finish off your problem set.